This is a video to help you prepare for the trigonometry unit that's beginning next. We're going to be looking at some of the basic vocabulary and ideas that make trigonometry understandable. Trigonometry is a word coming from Greek. The trig part comes from the word trigonon, which meant triangle, and metri comes from metron, which is Greek for measure, so triangle measure. Specifically, trigonometry deals with the patterns and relationships among sides and angles in triangles, usually right triangles, and the patterns and periodic relationships that sort of appear as you go through different cycles of rotation. Although we won't get to these actual functions today, this video will set the stage for these buttons on the calculator, which you may have seen since childhood, wondered, well, we've never used these buttons before, what do they really do? By the time we're done with the trigonometry unit, you'll have used them quite a bit in your math class. So let's go ahead and dive in. We'll start off with what appears to be a fairly easy question, and the question asks, where is the biggest angle in this triangle, the smallest, and the middle sized? The biggest angle would have to be the right angle here, because there's no obtuse angle here, so the biggest angle there. And the main reason I'm asking this question is for you to draw your attention to the relationship among the side lengths in relation to the angle. So the red angle is the biggest angle in this triangle, and you'll notice it is directly opposite from, or across from, the biggest or longest side length in the triangle. And you might think, well, maybe that's just a function of this particular one, but you can modify the shape and the relationship is still true. The biggest angle and the biggest side length are located directly opposite each other. On the opposite end of things, the smallest angle looks to be right here, the narrowest part of it, and it's directly opposite from the smallest side length of the three here. The red one's the longest, the green one is the shortest side length. You notice it's also true here. And finally, the one left over, the middle child, is not as big as the 90-degree angle, but not as small as this one over here across from the smallest side. So the medium-sized angle is located across from the medium-sized side length. So that's the main thing to draw your attention to here, is that the biggest sides and the biggest angles go directly in correlation to each other. That's actually not true only of just right triangles. You notice both of these are right triangles. That's true for any triangle. If you look at this modifiable image here, the smallest angle is always going to be highlighted here in pink, and no matter how I sort of tweak or warp the figure, you'll notice that the smallest angle is always across from the shortest side length. And if I make an angle bigger, of course that changes because there's 180 degrees in every triangle. And the same is true for the largest. Biggest angle, biggest side length, directly opposite. An important term to know when it comes to trigonometry is the variable theta. So let me write that out for you. Theta. That's also a Greek letter, actually. That's how it's pronounced. And the way theta looks is this symbol right here. We use it in math and science and engineering for angles, typically. We use other Greek letters too when needed, because sometimes you have more than one angle that needs to have a symbol associated with it. Sometimes we use alpha and beta, but theta is sort of the common one. You can kind of think of it as x as the common variable to use in algebra or for missing lengths. We use theta for missing angle measurements. So theta, be sure to keep an eye out for that. If you see that symbol, all it's referring to is the measure of that angle. So more terminology, the term opposite. This question asks, which side length is opposite from angle A? So the point of reference here is a key part of this. From the perspective of angle A, so if you were standing at this location, you have the three side lengths of the triangle arrayed in different locations relative to where you are. Right next to you is the side length AB, and directly across from you is the side length BC. And opposite is another way of saying across from. So opposite basically means across from. Who's sitting opposite you in class is your face partner, right? So the answer to this question, what side length is opposite from angle A? The answer to that question would be BC. And you see the importance of the point of reference there. If I instead ask, well, what's the side length opposite from angle C? From this perspective, go directly across, and that would be side length AB. So the point of reference is the key to understanding the relative notions of opposite, and as we're about to see, adjacent. As previewed, we'll also be looking at the idea of adjacency. Same picture, what side length is adjacent to angle A? So same point of reference, angle A. So from that perspective, adjacent means next to. Now there's a bit of ambiguity here because, strictly speaking, there are two side lengths next to the position at angle A. One can make a good argument for this side length being right next to angle A, and one can also make an argument for this side length being right next to angle A as well, because they both join to meet at point A. However, as you may recall from the Pythagorean theorem, this longer side has a special name all of its own, so rather than give it two special names, we assign the term adjacent to the shorter leg here. So the answer to this question, which side length is adjacent to angle A, that would be side length AB. So adjacent here again means next to. Finally, as mentioned again, sort of as a preview, that term that refers to the longest side of a right triangle, the hypotenuse. So this question says, which side length is the hypotenuse relative to angle A? And this is actually a deliberately misleading question because, if you recall, the hypotenuse by definition means the longest side of a right triangle. Longest side of a right triangle. And as we saw earlier, the longest side is directly opposite the biggest angle, and the biggest angle is the 90-degree angle. So this relative to angle A part is unnecessary. So it's important to realize that opposite and adjacent are relative terms. Where you're standing or where you're pointing reference to dictates what is across from and what is adjacent to. To go back a slide for a moment, AB is adjacent to angle A, but that very same side length is opposite of angle C. So what is adjacent from one perspective is simultaneously opposite from another. Because the, again, opposite of C was adjacent to A. But hypotenuse is a constant. It's not changing because of its definition. It's the longest side of a right triangle, and that doesn't matter where you're standing. It's always going to be the side length, in this case, AC. So the answer to this question would be AC, the side across from 90. Are these two triangles similar? Well, they sort of look alike. They both have 90-degree angles in them. And they also have this symbol right here, which hopefully you've remembered is called theta. And the fact that it's the exact same variable indicates that whatever this angle is in degrees or radians, then this angle must also be the same. So if you recall from our previous unit of study, that this is something called angle-angle similarity. When two angles and two triangles are congruent, the reds and the blues, then in this case the triangles are similar to each other, so yes. The reason I bring this up really is for the following. Let's say that this smaller triangle had three side lengths, and I'll just call them x, y, and z. So I don't know what x is, I don't know what y is, I don't know what z is. Let me actually relabel those. Let's call this y, x, and z. Just placeholders for some numerical value. Well, if this is similar, then there must be some way to scale up by some scale factor to make it a bigger shape, and we have established that they are similar. So there's some scale factor which will take the small shape and make it that much larger, or smaller, but in this case larger. So let's assume for a moment that the scale factor is some amount called k. So the bigger triangle is k times bigger than the smaller triangle. What that means is that each one of these three side lengths, which are again x, y, and z at the moment, would become multiplied by that scale factor. So just as an example, if these side lengths were scaled by a scale factor of 2, you would just multiply all the side lengths by 2. And if it were by a scale factor of 3, you'd multiply the side lengths by 3. But in general, we're just going to call that scale factor k, which means that this side length right here would be kz, whatever k was, times the original z. This side length would be whatever x was times that same scale factor, and this side length right here would be whatever y was times that very same scale factor. Okay, fair enough. That's not too groundbreaking, hopefully, but the reason I bring that up is this, ultimately. If I were to make a ratio among the sides of this triangle, and the reason I'm doing that will become more apparent in class, but bear with me for a moment. If I were to make a ratio of this small triangle, and that ratio would be comparing the two following things. It would be the opposite divided by the adjacent. And remember, those are relative terms, so I'm going to use theta as my point of reference. So from theta's perspective, what is the ratio of opposite to adjacent? Well, from theta, the opposite length is called y, directly across from that point of reference. And from theta, the adjacent length is called x, because that's right next to that angle of theta. So the opposite adjacent ratio for the small triangle is y over x. Well, this big triangle, if I'm using theta as well as its point of reference, then the opposite from this theta, so opposite over adjacent, if I were to compare these two values as in a ratio, the opposite length from theta is k times y, and the adjacent length, the leg that's not across from, but not the hypotenuse either, the other leg basically would be kx. So I have k times y times over k times x. And if you recall just from simple algebra or arithmetic, the k's would cancel here, leaving you with the very same result of y over x. And what this basically tells you is that when you have an angle, in this case, whatever theta is, however many degrees that is, then the ratio that's sort of affiliated with that angle is going to be a constant. It's the same ratio in both cases, even though the triangles have scaled up or down in size. And if some of that seems kind of abstract and unusual, you're not alone, I'm sure. It'll become much more clear why I bring this up now once we actually dive into the real nuts and bolts of trigonometry. I'll leave you with one last thing, which is an important term to know for trig, and it's called SOHCAHTOA. It's an acronym, and the capitalization here is a useful sort of tool as well, and there are 3 parts to it. And you'll be hearing that term a lot in class, so I wanted to put that in your brain this time. All right, I'll see you in class.